A translation is a transformation in which a figure is slid from one position to another without being turned. Remember that when a constant k is added or subtracted from a parent function, the result is a translation of the graph up or down. When a constant h is added or subtracted from x before evaluating a parent function, the result is a translation left or right. So simply put, thinking about back when you first did transformations with quadratic equations. G of x equals x minus 1 in parentheses squared plus 4. The number that is grouped with the x is your left-right shift. Since this is a -1, remember that it feels like it goes backwards. So -1 is actually a shift that is right 1. And then the number that is not grouped with the x is your up-down shift. It's a +4, so that is up 4. So with quadratic equations, you would take the vertex, the starting point, which is normally at the origin, and then go right 1 and up 4. That's your starting point. And then again, with quadratic equations, we can apply the 1 through 5 rule. So go out 1, up 1, from those points out 1, up 3. And if we have room, we would go out 1, up 5 from those points, and we would draw our parabola. So that is a shift using a quadratic equation making a parabola. We've been doing trigonometry parent functions lately, but now we're going to start shifting those. We'll start with the horizontal translation, and a horizontal translation of a periodic function is called a phase shift. So if you have a number that is grouped with either the x in a trig function or oftentimes theta in the trig function, that is your left-right shift. So looking down at the bottom of this screen for the examples, if it's y equals cosine theta minus 90, the minus 90 is grouped in parentheses with theta. That means it is a left-right shift, and since it's minus 90, this is 90 degrees to the right. Y equals tangent of theta plus 30 degrees. The 30 degrees is grouped with the theta. This is your horizontal shift. Since it's a plus 30, we will go 30 degrees to the left. These also work with secant, cosecant, cotangent graphs using the same rules, so they also have phase shifts, just like sine, cosine, and tangent. So example 1 is state the amplitude, period, and phase shift for y equals sine theta minus 90, then graph the function. Starting with the amplitude is just 1 because I don't see anything in front of the sine, so there must be a 1 there, so an amplitude of 1. The period, we will still use the period rules for sine and cosine, which is 360 degrees divided by the b value. I don't see anything in front of theta, which means there must be a 1 there, so the period is 360. And then it asks for the phase shift. And then the phase shift is going to be your horizontal shift. Since there is a minus 90 there, that means it is shifting 90 degrees. Minus 90 means it's going to the right. So our phase shift will be 90 degrees right. Before I graph the final function, I'm going to graph the parent function, which is just going to be y equals 1 sine of theta. So this is without the shift of minus 90 degrees to the right. And how do we graph sine of theta? So sine of theta starts at 0, 0. It has a period of 360, so it ends at 360. Has an x-intercept at midway between the starting and ending points at 180. Reaches its high point halfway between 0 and 180. Since we have a amplitude of 1, that will be 1. Reaches its low point of -1 between 180 and 360 at 270. So this is one full period of the parent function. But we are going to graph it after a shift. So in blue, I'm going to take every one of those points and I'm going to move them 90 degrees to the right. So the starting point at the origin is now going 90 degrees to the right. The high point at 91 will go 90 degrees to the right. It will now be at 181. That x-intercept at 180 is now at 270. The low point is shifted 90 degrees right to 360, and the x-intercept of 360 moves to 450. So this is one full period of the function with a phase shift. And we can follow those same patterns. So it'll have a low point down here at 0, -1. And here as well, if we wanted to continue the pattern for more than one full shift, it could look like that. State the amplitude, period, and phase shift for y equals 2 cosine of theta plus 45 degrees, and then graph the function. Okay, so the amplitude on this one, it does have a 2 in front of the cosine, so the amplitude is 2. The period, I still don't see a b value in front of theta, so that will be 360 divided by the b value of 1, which is 360. Phase shift, there is a shift. It is plus 45, so that is 45 degrees. Since it's plus 45, that is left, so 45 degrees to the left. So again, I'm going to graph the parent function. The parent function will be y equals 2 cosine of theta. So I still include the 2 with the parent function. I'm not going to include the 45 because the 45 is the shift. So 2 cosine of theta starts at the high point at 0, 2. A full period will occur 360 degrees later. Halfway between the highs will be the low point of 180. And then halfway between the 180 and the high points are the intercepts. So one full period in a red dotted line would look like this. And then we're going to graph and shift every one of those points 45 degrees to the left. So the starting point goes 45 left. It'll be right there. This point will go 45 left. This point will go 45 left. The 270 point will go 45 left. And the high point will be 45 left. So this will be one full period of the final graph. And I can continue those patterns as well. So there would be a point at -90 for the parent function. So 45 degrees to the left of that would be right here. And I continue to do the same way the other way. There would be a y-intercept or an x-intercept at 450. So if I shift that 45 to the left, that would place it right there at 405. It would go about like that. So that is more than one full period of 2 cosine theta plus 45 degrees.